Next up is Neel Patel, who's an MS student in the architecture research group at the University of Kansas. He's interested in memory systems and their performance impact on cloud and data center workloads. And he's here to talk about profiling Gem 5 using FireSim. Go ahead and take it away.
Hi, so my name is Neel. I will be presenting in lieu of our first author who unfortunately could not be here today. So
Click the screen again.
You can use the like. Just click on it. It has like a
it has a
yeah, a little clip. You just attach it.
If you want to try to click it as well.
So today I want to give some motivation on the agenda is I will start by giving some motivation for why we chose to profile an architectural simulator. Essentially, it's because software-based architectural simulation is widely spread. It's abundant, but it's also very slow. And a key observation in our work is that Gem 5 can run up to 1.7 to 3.7 times faster on a MacBook Pro with an M1 chip compared to a Dell server with an Intel Xeon Gold processor. So our initial goal was to extensively profile Gem 5 using hardware performance counters. And some initial insights we got from our profiling was that Gem 5 is front-end bound and it's sensitive to L1 cache size. So we wanted to use FireSim to compare Gem 5's performance with various L1 cache sizes. And our results were that Gem 5 performance, so simulation speed, can increase by up to 58% when increasing the L1 cache size from 16 kilobytes to 64. This is the outline for the remainder of the talk, but I want to start by giving some background on software-based architectural simulators. So as I said earlier, they're widely used, but they're quite slow. Some examples of software-based architectural simulators are Gem 5, ZSim, and Sniper. And Gem 5 is a single-threaded simulator that simulates at 0.1 to 1 millions of instructions per second, and which is quite slow, orders of magnitude slower than native hardware. So a lot of efforts have gone into reducing simulation time. Examples are sampling and checkpointing, FPGA acceleration, for example, FireSim, parallel and distributed simulation, so spreading the simulation out across multiple nodes, and trading off simulation accuracy for speed. So our initial observation was that Gem 5 runs a lot faster on these Apple M1 chips, even on a MacBook Pro. This chart shows the difference between the simulation speed on a Dell server with an Intel Xeon chip. The black bars are the minimum and the maximum, and the simulation speed of a MacBook Pro with a M1 chip. As you can see, the simulation speed in kilo instructions per second is a lot higher on the MacBook Pro, which was quite surprising to us initially. So our questions were, why does Gem 5 run faster on the M1 chip? Where are the bottlenecks in running a Gem 5 simulation? And how much faster can you make Gem 5 run just by changing microarchitectural parameters and system configurations? So I want to discuss the methodology we used to collect our results and then what some of our initial results were. So we decided to treat Gem 5 basically just as an application, and the parameters that we changed for the application itself were the different CPU types that were simulated using Gem 5, and then the parsec workloads that we ran on top of Gem 5. And we used hardware performance counters like through VTune and perf to collect our results. And here are the specifications for the two processors, the Xeon Gold, which is Skylake microarchitecture, and then Apple's ARM M1 chip. And just looking at these details, you could probably glean some insights on why the M1 chip might outperform the Dell server. the M1 chip has a 6 times larger L1 I cache and a 4 times larger L1 D cache. So we started by profiling the L1 miss rate, and we found that the I cache miss rate for the M1 chip is negligible, while there's a noticeable 10% miss rate for the Intel chip when running a series of Gem 5 simulations. And then there's also a noticeable difference between the D cache miss rate. And there's some more profiling results in an upcoming ASPLOS paper where we do more profiling on Gem 5 simulations. So the hypothesis is that Gem 5 simulation speed is very sensitive to L1 cache size, but how do you prove this? Obviously, running a software-based architectural simulator on another software-based architectural simulator would not be ideal. So we decided to accelerate this as part of our research using FireSim. So there's the series of steps we use to run Gem 5 on FireSim are here, but if you're interested in reproducing our results, you can check the link here and reproduce the first 5 steps and then collect the results. The system we used on FireSim was a quad-core rocket chip with a 16 kilobyte 4-way set associative I cache and D cache and a 512 kilobyte L2 cache. And then this is the base configuration. We modify the cache sizes during our testing. So we try 4 different I cache sizes and 4 different L1 D cache sizes and then 3 different L2 cache sizes. So increasing the D cache size by a factor of 4 shows speedups across all the different CPU types, or a few different CPU types you can simulate in Gem 5. So in order of complexity from left to right, you can see that all 3, the atomic, minor, and O3 CPUs see over 20% speedups in simulation time when increasing the D cache size. Increasing the I cache size doesn't have as much of an impact on the O3 CPU type, however, but the speedup is still noticeable. And then increasing both the I cache and D cache sizes can result in an over 50% speed up in simulation time for running Gem 5 simulations. Interestingly, the L2 cache size did not make as much of an impact. In fact, we didn't notice, there was no noticeable impact in the speed up for running Gem 5 simulations. So I want to cover a little bit of our experience using FireSim since it was our first time using it, and we were trying to collect some initial, and our experience is collecting initial research results using it. So it took us about 1 week to prepare the benchmarks for FireSim. We noticed that as expected, it's relatively slow compared to native hardware, but this caused us to incur some expenses. So if a Gem 5 simulation runs in like 2.34 seconds on real hardware, running it on FireSim can result in about a 118 times slowdown. And this, we also found that the usage model compared to a traditional software simulator is obviously a lot different, which can cause you to incur some expenses. For instance, the FPGA instances can cost between $1 and $9 per hour. So misconfigurations or failed compilations can cause you to incur some expenses. And when you're enumerating like a large design space or trying to test a lot of different configurations, it can become cost prohibitive, especially compared to like testing a large configuration space using software, traditional software space simulation. And then we found that we would fail in some of our configurations when we at the AGFI build stage. So we would pass the initial compilation to the RTL, but fail once we try to build our AGFI image. And then this could result in some costs as well. So you could lose I think we noticed failed FPGA image builds could cost between $6 and $52. So I want to conclude by giving a summary of how FireSim was relevant to our work and our work on profiling Gem 5 simulation. So we found that Gem 5 is front-end bound because of its large instruction footprint. And using FireSim was helpful because it allowed us to study the size of the iCache and Dcache impacts on Gem 5's performance. It was quite useful for enumerating a few important configurations and proving our hypothesis. And it also helped, it's also helped motivating our work for hopefully designing accelerators or specialized cores for simulation-based workloads. So if you want to reproduce our results or learn more about this project, you can check out the link. Thank you. Oh.
Oh, no, I'll walk up here. So can you speak a little bit about some of the workloads that you're running? So you mentioned that you saw kind of one performance number on the M1 Mac versus the Xeon. What workload was that running? Was that an average of a bunch of workloads? And then how did you actually like move that workload to FireSim? So I presume yeah, or I guess I'll start with that for right now.
Okay, yeah. So it is an average across a lot of parsec workloads and Splash for these charts. These are average speedups across a variety of workloads. And the steps we use to create the AGFI image were here and also at the link. If you'd like to see the steps or reproduce any of the results. I believe the workloads should be there. If they're not, we'll post them later as well.
Yes. Any other questions? So do you guys have ideas for other parts of the microarchitecture that you want to explore for their type of architectural simulator?
Definitely. I think we use this rocket core, which is in order. So we were hoping to actually also test out of order cores to see if that changes the so I guess the boom cores to see if that changes the impact of L1 size, because that should add some resiliency to like L1 misses. That's one thing we definitely should evaluate as we consider specialized architectures for simulation.
We talked about failed configuration builds and AGFI generations. Not really more common. It would be cool if we had like a pre-generated simu of like if people just want to be sweeping like standard rocket or architectures, if those just can. And people could say like, yeah, I want to sweep in the cache size or whatever, like normal parameters that people are sweeping. That'd be a cool feature.
Yeah, that would definitely be helpful for you. Would have been helpful for you.
Did you have to look at those looks? Like, do you know why the AGFI looks out of those?
Yeah, I actually looked into it yesterday with Abe. We were trying to figure out why one of our builds failed, and we found that the L1 cache size configuration we chose just was not allowed on the rocket tile itself. So I guess the set size we chose was incorrect, or not, like there are bounds on the so we noticed that the compilation didn't fail, but it failed at the AGFI build stage. Possibly.
So I think there's a combination of issues where in some cases the configuration is passing, but then the build itself is way too large for FPGA, and so it's very rare. That's one set of issues, then the current issue that was set here is before they do by that stage, it's during stall operation. So.
Okay, that makes sense.
Any conclusions or insight that you can draw from your relations? You can basically take to the Gem 5 development, say, change this and that to maybe reduce the number of instructions they're using, make it faster for regular distance.
So we have some system configurations that we tested outside of this that we found helped with improving Gem 5 simulation speed, like using huge pages and things like that are covered in the paper. But generally, it seems that the CPU complexity impacts performance a lot just because of a lot of indirect branching and instructions or indirect branching and large instruction footprint. So we haven't given any feedback to Gem 5 developers in that regard, but more extensive profiling of the code itself would definitely be something to investigate. And hopefully we'll do that in future work.
Any last questions? Thanks again.
Thank you.